All right, welcome back, friends. So now we're going to continue on talking about water and why it's so unique and some of the really interesting aspects of it. So we're going to start with, if you recall back to the previous video, and what we ended on was talking about temperature and heat, right? Remember that temperature is how much heat an object has, and then heat is the amount of energy that is coming from an object, which and there's heat transfer, right, between warm objects and cold objects, and heat goes from hot to cold, right? If you have a cup of coffee or a cup of tea and you're holding your mug to your hands, you are actually correct in that you're warming your hands up with that process. But then in the opposite way, if you were to stick a piece of ice into that tea or coffee to cool it down a little bit, your drink is actually warming up the ice. So kind of weird. But speaking of ice and molecules moving, and I kind of ended on talking about atoms and how fast or slow they are in comparison to the warmer the object, the faster the atoms vibrate, the colder the object, the slower they vibrate. And so when we consider visually looking at that with water and the three states of water that occur naturally on Earth, this is what we would see, right? So as a solid state, the atoms are not moving, right? Whereas in the liquid state, the atoms are moving at least a little bit more than they were in the solid state. And then a gaseous state, the molecules are super, super, super excited. So they're going all over the place, and they're like, and they're bouncing all around. They're super, super stoked. So that kind of, in a sense, finishes that up a little bit. And now that we're considering the three phases of water that occur naturally on our planet, we need to now consider how much energy it takes to go from one state to another. And you've probably actually experienced almost all three versions of water on our planet. Water vapor as a gas, that's literally just feeling humidity. Water as a liquid, any sort of ocean or a body of water. And then water as a solid. And in our atmosphere, this actually exists as, say, snow or ice crystals. Closer down to land, we have like icebergs and sea ice, glaciers, any sort of ice just in general. So that's kind of all of that there. And then when we're considering, how much energy it takes to go from one state to another, there's a couple of terms here that we're going to introduce, and they're similar to a point, but they have some differences. So this first term is called latent heat. So latent heat is the heat that is required to make a phase change. So we're going from, say, a solid to a liquid, or a liquid to a solid. So it takes a certain amount of energy to do so. It's also known as the heat that is held in storage. So that term latent is you're storing it away somewhere and you'll release it later on. So the big thing to take away from this is the latent heat of the process of melting or freezing, is only 80 calories, whereas the amount of the latent heat for vaporization, or condensation is much higher, to 540 calories. So the unit that we're using here is calories, basically meaning that you can think of back to food, right? We ingest calories when we eat calories, and that gives our body energy to continue on doing its body stuff, right? So similar sort of idea. So in terms of the amount of energy that it takes to for these processes to occur. So the biggest thing here is that it takes so much more energy to condense or vaporize than it does to melt or freeze. And you can think of it this way, like to go from room temperature water to boiling water takes a long freaking time, and then when you're boiling the water, then you're releasing water vapor. Whereas if you are you just you want to freeze water, it just does not take nearly as much energy. You can just stick it in the freezer and call it a day. So this is another graphic kind of trying to show this a little bit. So if we're going from ice to liquid, it's a warming process. It's melting, right? So you only have to add 80 calories for that. If you were to stick an ice cube just out on the counter and just let it be, then it's just going to melt on its own if it's not in a freezer, right? But if you wanted to go from the state of water, liquid water to water vapor, you got to add so much energy into that. And even going from, like 100 degrees Celsius water to water vapor, you're going to add another 540 calories. In the negative, or in the opposite direction, it's basically the opposite. So to go from water vapor to condense down into water, you have to take out 540 calories, and to cool the water down, you remove another 100 calories, and then to freeze, you only remove 80 calories. So it's really just trying to show this idea here. It's a little bit funky, so if you're like, what the heck, it's okay. If it's your first time hearing this or seeing this, don't worry, it's all right. You might need to revisit this idea a couple of times. And another way to kind of visualize this in terms of a graph here, just to really bring home this idea that going from a liquid to a vapor takes a ton of energy. On our x-axis is calories, and on our y-axis is temperature. Right, so if we're in ice, if we start as ice, notice how the distance between A and B is so much shorter than the distance from C to D, right? So it takes much more energy to go into the vapor phase of water, all right? Then, hang on one sec. And then the next little concept here, instead of latent heat, now we're going to talk about specific heat. So specific heat is the heat that is required to raise the temperature of 1 gram of material by 1 degree Celsius. So the specific heat of ice is 0.5 calories per gram. The specific heat of liquid water is 1 calorie per gram. And the specific heat of water vapor is 0.44 calories per gram. So the big take-home point here is that liquid water has almost double the specific heat potential as compared to water vapor or ice. So again, think about like when you try to heat something up, like you're boiling a pot of water or something for some pasta, or you're making some tea or coffee. It takes a long freaking time because you're trying to raise the temperature of that material, certainly by more than 1 degree if you're trying to make it boil, but just how much energy goes into it. Another way to kind of think of that, and another term for it in a sense, is heat capacity. So water has an extremely high heat capacity. And that depends on the specific heat and the mass of the material. And so basically what this is trying to say is that water can take in or lose a lot of heat without changing much of its temperature, which is kind of weird to think about, right? Especially when we're considering what we think of when we hear the word heat and temperature. We got to remember that there's a difference here, right? At the graph here on the right-hand side, these are some different substances that Earth has and the different heat capacities, including the different phases of water, have the different heat capacities here, right? So pure water versus ice versus salt or granite or mercury, right? So the lower the specific heat capacity, the less energy it takes to warm that up, right? So again, kind of going back to the idea of boiling a pot of water. If you have, you have maybe a copper pot it's not going to take a whole heck of a lot to get that copper nice and warm, right? You put it on the stove over, electric or fire, and it doesn't take very long for that pot to warm up, but it's going to take a while for the water to boil. That's kind of an analogy that you can use or think of there. And then you're like, why does this matter? Who cares talking about this? Well, it has actually a really, really huge impact on local temperature variation for different locations. So maybe you've wondered to yourself at one time, like, why do we never get snow here in San Francisco or in the Bay Area? Or why does it not get super, super hot in the summertime? Well, it's because we have that sweet, sweet, sweet Pacific Ocean right there, which acts as our natural air conditioner. So in the next video, we will go through and look at the differences in between 3 different locations across the country at the same latitude that experience markedly different temperature variations. So hang tight and stay tuned for the next video.